before going for the second session, I would like to make a small announcement. This is to remind you that there is a dinner at 7:30, banquet dinner at 7:30 here. So all of you are invited for that. So our Jean-Francois Lafont, who is going to talk about 4-dimensional locally cat-zero manifolds with no Riemannian spooling.
Okay. So I'd like to thank the scientific committee for asking me to speak. So what I'll be talking about is some joint work with Mike Davis and Tadeusz Januszkiewicz. So the framework is a bit of the following. So as everyone here certainly knows, there's much interest in Riemannian manifolds with sectional curvature less than or equal to 0. So this is a vast subject that most everyone here is somewhat familiar with. And then there's been, so motivated by this, there's been metric notions of non-positive curvature that have been introduced. So the cat-0 metrics form a metric version of non-positive curvature. Okay. Now, if you're interested in topology, and I might have a biased viewpoint, the basic objects of study are manifolds. And so one question you could ask is whether this notion, so cat-zero metrics for the class of manifolds, gives you anything wider than just Riemannian non-positive curvature. So here's a basic question. Can people see? Should I move the bottle down? So basic question is to try and quantify, or what's the difference for manifolds. What is difference between supporting, so locally cat-zero metric and supporting a Riemannian metric with non-positive curvature? Okay. So obviously, if you've got a Riemannian metric with non-positive curvature, you get a locally cat-zero metric. So the question is really about the converse. So a few remarks. So in low dimensions, there's no difference. And it's work of Mike Davis and Januszkiewicz that in high dimensions, so this is greater than or equal to 5, there is a difference. And I'll say a little bit about so there is a difference. So i.e., there exist closed manifolds M supporting metric non-positive curvature but do not support Riemannian non-positive curvature. Okay. So what I want to talk about today is the missing case, so dimension 4, and these new examples that we've constructed. So before I do that, let me give you some idea of how these high-dimensional examples are constructed. So previously known obstructions. So these are previously known obstructions to having a Riemannian metric of non-positive curvature. And these kind of fall into two categories, which I call sort of topological as opposed to geometric. So on the one hand, you've got topological obstructions. So to explain that, So there's various categories you can work with. And in order to have a Riemannian metric of non-positive curvature, you need a smooth manifold. But when talking about manifold topology, you can also just talk about a topological manifold or a PL manifold. And there exist examples which are non-smoothable. Okay? So these are the topological family of obstructions. So there exist examples of non-smoothable compact manifolds. So I'll always be restricting to compact manifolds. If I leave that out, mentally insert that word. Compact M, which support a locally cat-zero metric. And so in particular, those manifolds won't support any Riemannian metrics because they don't even support a smoothing. Okay, so that's the topological, and there's, within there's various different types of examples you can look at. At the other extreme, there is sort of a different viewpoint, or sort of geometric obstructions. So let me give you a couple examples of this. So the geometric obstructions, so the basic version is the Cartan-Hadamard theorem. Tells you that, so if you have a Riemannian smoothing, then the universal cover must be homeomorphic to Rn. In fact, diffeomorphic to Rn. That if Riemannian metric exists, then M tilde is diff to the appropriate Rn. Okay. Well, now there exist examples. So again, there exist examples of locally cat-zero manifold, locally cat-zero manifolds with M tilde distinct from Rn. Okay, so again, these things would not support Riemannian non-positive curvature. Now, slightly more sophisticated than this. So this property of having the universal cover being homeomorphic to Rn can be interpreted in terms of the boundary at infinity. And this corresponds to the boundary at infinity, well, being simply connected. So simply connected at infinity is forces the universal cover to be Rn. So other types of obstructions that come out, well, again, if you've got a Riemannian metric with non-positive curvature, the universal cover should have boundary at infinity as sphere. So that's another type of geometric obstruction. So there exists, so also there exist examples with the boundary at infinity of M tilde distinct from a sphere. Okay. Sorry? But not necessarily. Yes, there exist. Right, so there exist examples which don't fall into this previous. Yeah. Okay. And then, so one last method is a reduction. And this is, so if M, so is a locally cat-zero metric which is non-smoothable, is already an example. Then M cross N, where this here is cat-zero, so locally cat-zero, is also an example. So here, when I say an example, I mean of something which is locally cat-zero, but does not support Riemannian non-positive curvature. And the reason for that is you've got splitting theorems, and in the Riemannian setting, if you've got something that splits, then the factor is also Riemannian. Okay? So applying that to this gadget here, if this had a Riemannian metric, you can use that to deduce that M would have one as well. Okay. So these are sort of at least the obstructions I know of. And so now what I want to talk about is a little bit of this, our new constructions. And the new construction falls into a geometric type of obstruction, which uses, which exploits the structure of flats. Okay. So yeah, all of these things. So all of the examples, both in topological and the geometric approach, only exist in dimensions 5 and above. And some of these, so for example, the topological, you need to go higher than 5. I guess like maybe 7 is the smallest for topological non-smoothable. And yeah, I mean, there's some dimensions constraints in which these exist. Let's see. So in dimension 4, I don't think so. No, I don't know if examples there. All right. So what's the idea behind our construction? So the basic idea. How am I doing on time? Okay, not too bad. So the basic idea is this. And then I'll gradually fill in more details as we go along. But so the basic idea is this. So we want to construct. A smooth M4, and this will be equipped with a locally cat 0 cubical complex structure. So here I mean you've got a decomposition. So cubical complex, each cube is given, the standard 0, 1 product metric, but the whole thing is locally cat 0. So this is just a condition on the lengths. With the property that there exists a 2 torus so this is going to be a flat 2 torus. So the embedding here is isometric. Such that, and a point so I'll identify the T2 with its image. So point P in T2 inside M4, such that the local picture is knotted. So if you look at the link at the point P, so the link at the point P, so inside the 2 torus T2, so this is going to be a copy of S1 sitting inside the link inside M4, the point P, so that's going to be a copy of S3. And this defines a non-trivial knot. Okay. Now, assuming we can do this, let me go ahead and give some idea. I need one other. Yes. So this will be a cubical subcomplex. So in fact, cubical subcomplex. Yes. And I need one other. And I need one other condition. The universal cover, so M4 tilde, satisfies the isolated flats condition. So this was introduced in Chris Kruska's thesis. So now let me explain why, if you had this, so if you can construct such a manifold, the claim now is that this does not support any Riemannian metric of non-positive curvature. So let me maybe first go ahead and argue that, and then I'll explain how we go about constructing this. Okay. So let me claim. So such an M4 cannot support a Riemannian metric non-positive curvature. Okay. So there's kind of two steps to this. There's a local to global and then a global to local. So let me maybe talk about how this breaks down into two steps. So first, the first step is, well, you can look at a lift of this torus. So that gives you a flat in the universal cover. So consider, so F inside M4 tilde, the two flat obtained as a lift of this torus. Then the boundary at infinity of F defines a non-trivial knot in the boundary at infinity of M4 tilde. And so there's some, yes, totally geodesic implies that it's pi1 injective. And in this case, this is actually known to be topologically an S3. So this is follows from some earlier work of Mike and Thaddeus. Okay. So this here is telling you that the local knottedness, so you've got this point. So of course the local picture survives in the universal cover. So you've got this flat that's knotted at some point locally. And this tells you that this knottedness propagates to the boundary at infinity. Okay. And then the second step is coming back in. So the second step is, so for any other equivariant metric, so locally cat-zero metric. So how do I want to say this? So maybe, let me say it this way. So if there exists a Riemannian metric with non-positive curvature on M4, then, so corresponding to this torus gives you a z squared in the fundamental group. The z squared gives you a flat torus for this other metric. So we can look at the analogous flat in the universal cover. F prime. So this is corresponding to the same torus. So I don't want to say, I guess I want to say the torus freely homotopic to this one for your new metric. To the torus in the same topic class as this original one here must still be So at this point, you've got a contradiction. So I don't know. So from the boundary at infinity, it must be knotted, but from the Riemannian metric, it must be unknotted. So, so cannot exist. So let me put it this way. So maybe, yeah, maybe let me just do the second step first, because, so yeah. And then I'll focus on the first step, and then I'll talk about the construction. So what do I mean that, so why can it not exist? Well, on the one hand, so for 2, well, if you have a flat inside a Riemannian manifold, so for a flat f prime inside, so now M4 is assumed to have Riemannian non-positive curvature. So, well, M4 tilde, so with sectional curvature non-zero, Riemannian metric, flats are locally unknotted. Right. But if you look back here, we assume that M4 tilde satisfies the isolated flats condition. And that tells you that the boundary at infinity is actually well defined. Okay, so in general, for a cat zero space, you can have the same group acting on 2 different cat zero spaces where the cat zero boundaries are distinct. Okay, so the boundary at infinity for a cat zero space is not an invariant of the group. But if you know the isolated flats condition, then it is. Okay. So on the other hand, so there is an identification. So the isolated flats conditions, maybe I'll call this the IFC. So work of Grushka and Kleiner implies that because of the IFC condition, the boundary at infinity of so M4 tilde is the same for these 2 metrics. So it's well defined. Which in turn, so this uses the isolated flats condition, which in turn tells you that the boundary at infinity of f prime is knotted. So it's a non-trivial knot. But in Riemannian non-positive curvature, geodesics never branch. If you've got a geodesic, it extends uniquely. So the map from the boundary at infinity of m tilde, so the pair boundary at infinity m tilde, boundary at infinity f prime. So this is the geodesic retraction onto the local picture. Question? Yes. In this other metric, yes, yes. So.
You have to homotop your singular flat to a non-singular flat. There's some
right.
Strong version of that.
Well, but there's kind of 2 different metrics floating around. So a priori.
F is, why can't the boundary of F still be knotted?
Why can't the boundary of so the boundary of f is knotted in the boundary at infinity. And what I'm saying is this hypothetical f prime, which is homotopic to it, so freely homotopic to it, and is a flat in this other metric, still has to be knotted at infinity.
Right, so you have to prove that, for flat F, there is a flat in M4 with the smooth metric homotopic to F.
Yeah, that's the flat torus theorem, right? So yeah. So yeah, it's all right. Existence of flats can be detected by the fundamental group, and there's a z squared because this is an isometric. Is that okay? Okay. So here we've got a geodesic retraction from the picture at infinity to the local picture. So this is, the tangent space. So tangent space at a point. Tangent space. Maybe I should do it this way. So TP M4 tilde and TP F prime. Well, this here is an unknotted picture. This here is knotted, but geodesics don't branch. So this is a homeomorphism. So this is a homeo. So because geodesics don't branch. And so you've got a contradiction. Right? You've got a homeomorphism from something that's knotted to something that's unknotted. Okay. All right, so now let me explain point 1. So point 1 now, we want to go from a local knot to a global knot at infinity. So let me draw you the picture here. So you've got, so this is supposed to be the boundary at infinity, M4 tilde. So of course, imagine bumping up a few dimensions. And then somewhere in here, you've got a flat. Okay, so I'm going to maybe, well, let me just draw the flat as being at the equator. And somewhere inside the flat, you've got this funny point where you've got locally a knot. Okay. So here, this is a point P. Here it's locally knotted. Okay. And again, you've got a geodesic retraction map from the boundary at infinity to the local picture. But now you've got a singular metric, so geodesics can branch, so that map is not a homeomorphism. Okay. So in this situation, so we still have geodesic retraction, but this is not a homeomorphism. Okay. Nevertheless, so if you knew it was a homeomorphism, you'd be done, right? Because here the local picture is knotted, so then that would tell you the global picture is knotted. But it's not a homeomorphism. On the other hand, it's not too far from a homeomorphism. So in fact, but it is so close to being a homeomorphism. So it is a, well, so there's various statements I could put here. Let me say it's this. It is a near homeomorphism. So one can show that. So this uses some manifold topology. It's a cell-like map, and so you can show it's a cell-like map, so point preimages are contractible, and then that can be used to show that. So then it's known that cell-like maps are near homeomorphisms. So i.e., for this geodesic retraction, there exists arbitrarily, so it can be approximated. There exists, let me maybe move up here. So one can approximate this geodesic retraction map arbitrarily closely by homeomorphisms. Okay. So one can approximate this map arbitrarily closely by homeos. Okay. Now, so not only that, but in fact the same statement holds for any, if you look at any open subset in the local picture, so we've got boundary at infinity of M4 tilde going to the link M4 tilde point P. If you take any open set here, you look at its preimage under this, the same statement holds for the restriction of this map rho to rho inverse of U. Okay, so all these restrictions here can be approximated arbitrarily closely by homeos. So in particular, so we know that this map, so restricted to any open set in link M4 tilde P, you have rho from rho inverse U to U is at least a homotopy equivalence. So now that you have that, well, how do you detect that something's knotted? Well, you just need to compute the fundamental group of the complement. Okay. So now we want to compute pi 1 of, so let's see, the boundary at infinity of M4 tilde minus the boundary at infinity of this flat F. Okay, this is the locally knotted flat. And in particular, you want to show that, so you want to show that this is distinct from Z. Okay. Well, let me now take a little bit of the local picture here. So the local picture near this point P is that of a knot. So at P, so this is link VP. Oops. So here you've got a non-trivial knot. Let's see, I'm always going to mess up drawing the trefoil. So I won't. So here there's some non-trivial. Let's see. Is that a trefoil? It's some knot. Okay. So you get some local knottedness. And now what you can do is you can look at a tubular neighborhood of it. So you take a decomposition. So you look at a little neighborhood of the knot. So take U equals neighborhood of the knot in link in the local picture, so link M4 tilde P. And then V is, again, a complement of smaller closed neighborhood of the knot. Okay. And then what I want to do is I look at the preimages of those sets under this rho inverse of U. Okay, so call U sub infinity, V sub infinity preimages under rho of these two sets. And then you can decompose this gadget whose fundamental group we're trying to understand using Seifert-Van Kampen. Okay. So Seifert-Van Kampen gives us so that the pi 1 of this gadget we're interested in, boundary at infinity M4 tilde minus boundary at infinity of F, is given by pi 1 of U infinity pi 1 of, so let's see, so V was the complement of a smaller closed neighborhood of knot. So there we want to actually throw away the boundary at infinity of the knot. So V infinity minus boundary at infinity of F. And then this is over pi 1 of, so U intersect of V infinity. So this we know is a Z squared. Now, if you restrict to, let's see, what do I want to do? Oh, actually, I want to take u infinity minus, sorry. So u was the neighborhood of the knot. So u infinity will contain the boundary at infinity of f. Sorry. Swap that around. Okay, so now what do we know? Well, we know that restricted to open sets, we've got a homotopy equivalence. So we know for sure that this thing here is, you know, is a knot group. So the fundamental group of a non-trivial knot group distinct from C. So how could we conclude? Well, if we knew that this group here injected into that, then you'd be done. Okay. So you've got something that's non-abelian injecting into this guy. So that group has got to be non-abelian, so it can't be Z. Okay. All right. So what happens here? Well, you're taking an amalgamation, so the only thing that could conceivably happen is you'd be killing off some elements. So some elements here might get collapsed down in this factor. Okay? So it's enough to show, so this follows from, so if one had the map from pi 1 u intersect v at infinity to pi 1 u infinity minus boundary at infinity of f, injective. Okay. Then nothing gets collapsed down. This thing survives in the amalgam. Okay, so now this, though we can analyze quite easily. So now let me just draw a little bit of the picture near the knot. So you've got this situation. So I'm going to draw the knot unknotted just for simplicity. So you've got sort of this, the knot here is this core. So this is the knot. Okay. And then we've got the corresponding picture at infinity. So this here is the local picture. Well, or maybe I should call this, let's say this is the, let me do this, the picture at infinity. So this set here that I just drew is this u infinity, which contains infinity. And then what's this u intersect v infinity? Well, this is just, so if you think of this as being a torus minus the boundary, the u intersect v infinity is really a small neighborhood of the surface of the torus. Okay. All right. So now, what can happen? Well, if you think of how the fundamental group is generated, so you take an element in pi 1 of this u intersect v infinity, and you can write it in terms of the two canonical generators, so the A and the B. So we can write this as AB. Okay. And the first thing you observe is if you map it down, so this is the map rho. Here you've got the analogous picture here. So the map rho is a near homeomorphism. So anything which includes, which has a non-trivial coefficient in this direction will survive. It cannot bound. Yes? So if element is in the kernel, then v equals 0. On the other hand, so now you can just assume that the element in U intersect, so this is some curve that's close to the boundary. You can assume that the curve that's close to the boundary, or on the boundary, kind of loops around in this direction a bunch of times. And now what you want to know is when you push it down, can it bound? But remember, it's got to bound in the complement of this circle. Well, you perturb everything a little bit so that it's a homeomorphism. Then it has to bound in some slightly perturbed circle, complement of a slightly perturbed circle. But here the linking number with the core is non-trivial. And if you do a slight perturbation, you approximate by homeomorphism, linking numbers aren't changed. So you'd still have a non-trivial linking number, so it cannot bound in the complement. Is that okay? That went by a little bit fast. So looking at linking numbers, you can force A to be equal to 0. Okay. So this map here is injective, nothing gets killed. This non-abelian group survives in here. Okay. All right. So now, at 15 minutes, so let me say something about how this manifold is constructed. Any questions so far? Seems reasonably okay. All right. So to construct this manifold, what we use are right-angled Coxeter groups. So these are groups generated by finitely many involutions, many elements of order 2. And the relations are either, so the only relations, are generators commuting. Okay. So given any two generators, either they commute or there's no relation between them. Now, so the group is completely encoded, so this is encoded by a graph, so you can just stick a vertex for each generator, connect them up by an edge if the two generators commute, otherwise don't connect them by an edge. And that gives you all the data you need to construct one of these. And these have a number of nice properties. So such a group has an action, on a cubical complex. So this is called the Davis complex. Davis complex. And so now the trick is to try and, so our construction, so we want to pick this graph, which will give us our group, in such a way, so a group, so that the quotient of the Davis complex, so that M4 is given by this Davis complex, so let me call it maybe X, so X mod gamma, where gamma will be is finite index torsion free. Torsion free in the right angled Coxeter group. Okay, so you can always find such a subgroup. So let me maybe, let's see, how do I want to, so yeah, let me say a few words about how all of this goes. So maybe I'll draw one picture of a Davis complex, and you'll see what the general idea is. So you take the graph. So So the Davis complex. And then once I've shown you the picture, the properties we want for the graph will hopefully be plausible at least. So construction of Davis complex. So what you do is the following. So you've got this graph. So from graph G, you consider a cube consider a cube del of dimension, so cardinality of the vertex set. Okay, so this is minus 1, 1 to the cardinality of the vertex set. And now what you do is, so we consider, so take a cubical subcomplex of this cube consisting of so if you've got a cube of dimension indexed by the vertex set, to any face of the cube, you've got a naturally associated subset of the vertex set, namely the set of directions for that face. So what you want to do is you want to take all faces which correspond to a click in the graph. So correspond to a collection of vertices all pairwise adjacent. Okay. So anytime in the graph you see however many vertices that are all pairwise incident to each other, you look at the faces spanned out by those corresponding directions, and you throw them into this subcomplex. Okay? So the quick example is this. So this is one of the standard ones. Okay. So let's say that's your graph. So you take a three-dimensional cube. You've got three vertices. And then what you do is, so if I call this 1, 2, 3, maybe these are directions 1, 2, 3. So then all the faces that are parallel to 1, 2 get thrown in. So you get this front face, and then this. So this back face. Maybe I'll use a different color for that. And then you've got these. So what else is left? Then you've got all the edges in here. And then the Davis complex is just the universal cover of that. And the action is each generator acts by reflection in the corresponding direction. The way this is defined, it's invariant. It lifts. It gives you action of the corresponding Coxeter group on the universal cover. So if you were to draw the universal cover of this, it would look like you have a square. All right, so now what are the properties that we need for the graph in order to have these corresponding properties for the x, for the corresponding Davis complex? Well, we want a four-manifold. So let me put in a comment. So the link of vertices is, so the simplicial complex you get by filling in all simplices. So inside your graph. So anytime you see, I guess n plus 1 vertices that are all adjacent to each other, you glue in a face, n simplex. Okay. So, and the link of the vertices in Davis complex is, well, the simplicial complex, maybe the full simplicial complex with one skeleton. So here full, I mean every simplex that possibly could be in there is in there, with one skeleton given by the graph. Okay. All right, so if you want a manifold, then what you're looking at is a triangulation of the three-sphere. Okay. You want the link at the vertex to be an S3, so you've got the one skeleton of the triangulation of the three-sphere. So for manifold, so now what I'm going to do here is I'm going to list out the various properties we want our four manifold to have, and I'm trying to translate them into properties about a triangulation. So this is, sorry? So the link of a vertex, I mean the points, so inside the Davis complex, the vertices of the cube. So if you look at any of these, the link there is naturally a copy of, so on the one hand, that arc, and then a single point, which you notice in this case is exactly the full subcomplex, the full simplicial complex corresponding to that graph. Okay. All right. So now let me go ahead and translate some of these properties we want for our manifold into properties of the triangulation, and then I don't think I'll have time to explain how the triangulation is constructed, but if you're interested in that, you can look up the paper. It's on the I think it's on the archive. I think I posted it. So for manifold means you want triangulation of S3. Okay. All right, flat in a four manifold. So two-dimensional flat is going to be a four cycle inside the one skeleton. So if you think of a four cycle, if you do this construction for a four cycle, so you've got these generators, and you can rewrite this maybe slightly better this way. So you've got, let's see, these two guys that commute, these two guys that commute. Well, or rather, let me put it this way. These two guys that don't commute, so they generate an infinite dihedral group. These two guys don't commute. They generate an infinite dihedral group. And everything here commutes with everything there. So this gives you a d infinity cross d infinity, which is virtually a z squared. Okay. So four cycles. So four cycles in the one skeleton. And here by four cycles, so it's important that none of the diagonals be in there. Okay? Neither of these edges are allowed. So knotted, so locally knotted, well, I explained back here how you can think of the local picture at a link is given by, the subcomplex, so the simplicial complex, the full simplicial complex associated with the graph. So locally knotted means that the four cycle inside this triangulation is knotted. Okay, so you want a triangulation of S3 with a four cycle which is knotted. So then what are the other conditions that we needed? So an important one, we want the cat zero condition. Zero condition for X. So this is known to be equivalent to the triangulation being flag. Meaning that anytime you've got a n-tuple which is pairwise adjacent, that it actually contains the simplex planned out. And then finally, let me put last condition is this isolated flats condition. And this is, so here we're using some recent work of Capras. So this is equivalent to what we call the isolated squares condition. So a force cycle with none of the diagonals present is going to be called we call those a square. Okay. And the isolated squares condition is any two squares are disjoint. Now, so then the challenge is to construct such a triangulation of the three-sphere. And I'm just about out of time. But just to give you an idea, you start out with the knot you want to realize as a force cycle in S3. You subdivide it into 4 arcs. Then you take a little neighborhood of it. You pick some arbitrary triangulation outside of the neighborhood. Then you want to try and construct a flag triangulation with no squares outside of that little neighborhood. And for that, we appeal to some work, some recent work, I guess building on some stuff of Granichnikov. So recent result of Prasad and Svetkovsky. So I'm probably mangling the name. But so anyway, so that can be used to ensure that there's no squares outside. And then we sort of extend back inwards in the most obvious manner and check that you still have this isolated squares condition. Okay, and I'm out of time, so I'll stop here. Yeah. Yeah. So, well, I mean, it should be. I guess I haven't explicitly. The thing is that at infinity, at infinity, what the knot at infinity kind of looks, because you've got periodicity under a z-squared action, it looks like an infinite connected sum of this knot, of the knot you start out with itself. So, and actually, I guess it's not obvious that different knots will give rise to different things at infinity. That'd be the obvious way to go about it. So, but probably. Sorry. Yes. So, I think the question was whether we get infinitely many distinct. Well, but at infinity, it's a highly singular object, right? I mean, so locally, yes, but at infinity, you're if you think of larger and larger spheres, every time you pass through a copy of the singular point, you tack on a connect sum. And, right? So you're asking whether you can recover the knot structure from. Presumably, I guess, unless, let's see. Yeah, I guess you could switch the triangulation. That's one way to go about it. But I guess if you're asking whether you can get different knots at infinity, then that's not clear. But yeah, because you take your triangulation and you can always further subdivide it or further apply this Prasad-Svetkovsky procedure. And yeah, so in that sense, yes. But it'd be nice if one could get kind of genuinely different behavior at infinity, and that is less clear. So, other questions?